Jai Hind, welcome to the course Network Analysis and Synthesis, and today I am going to discuss about the Telegen's theorem applied to a electric circuit or network. So first and foremost I will discuss the theory part of this theorem, and later on we will discuss some examples related to the Telegen's theorem. So what is Telegen's theorem? So Telegen's theorem basically it tells that the summation of instantaneous power of all the branches in a network is 0, and this theorem is based on Kirchhoff's laws, Kirchhoff's KCL and KVL. So basically the proper statement of this theorem is, if a network having n nodes and b branches with instantaneous branch voltage and instantaneous branch current, say it is Vk and Ik. Vk, k is the branch number of the network, and Ik is also k is the branch number of network. So V is the voltage of that branch and current is also of that branch respectively. Then Telegen's theorem, we can have Vk Ik, product of Vk Ik, we take a summation over k is equal to 1 to b. So b is the number of branches in a network. Is 0 provided Kirchhoff's current law and voltage law are satisfied. So this is the statement of the Telegen's theorem. So what is the importance? Why we use the Telegen's theorem? Basically, if this theorem is applicable to check the topology of a network, if this theorem is verified, suppose we have taken two networks N1 and N2, and we verify the Telegen's property, then both the two networks will have the same topology. So just to identify the topology of the network, we apply this Telegen's theorem. So this is the second part is very important. The summation of instantaneous power in a network is 0 provided Kirchhoff's voltage law and current law are satisfied. So this is the statement of the Telegen's theorem. Now there are two properties associated with this theorem. So first we will discuss this property, and then we will come to just solve some problems. So suppose if two networks, say N1 and N2, N1 and N2 having the same oriented graph with the same reference direction assigned to branches in the two networks, but with different element values and kinds. What does it mean? So just suppose take two networks N1 and N2, and in N1 branch we have suppose a resistor, but in network N2 in the first branch we can have the resistor. So different element values, inductor of having the 1 Henry and resistor having the 100 ohm. So different element values and kinds. Kind means if the first branch of network N1 having the inductor, the first branch of N2 can have a resistor. Okay, and let V1K and I1K. So here V1K, this one is N1, okay, and K is the kth branch. So voltage and current of network N1 of kth branch, and V2K and I2K be the voltage and current in N2, where the all branch voltage and currents satisfy Kirchhoff's current law and voltage law. Then from the Telegen's theorem we can have this V1K, I2K. So product of V1K and I2K is equal to 0. And summation is over, K is equal to 1 to B. So, and here this is the V1K of network N1. Please be careful. So it is the kth branch, voltage of kth branch of network N1, and I2K is current of network N2. So take the same branch number of the both the networks, and voltage of this network N1 and current of network N2, and same way we can add from K is equal to 1 to B. B is the number of branches in the both the networks. Both the networks will have the same number of branches. It is coming 0. And V2K, here the voltage of network N2. This is the voltage of network N2, and this is the current of network N1. Branch number is same. We have taken the voltage and current of different networks. It is coming 0. So basically this property is required to check whether the two networks N1 and N2 having the same topology. So this theorem is applied to check the topology of two networks. If these conditions are satisfying, then both the networks are having same topology. So this is the first property of the Telgen's theorem. Then there is a second property of this theorem. If the voltages and currents are evaluated at two different instants of time, it still follows that Vk. So take the kth branch of the network, okay, of the same network, measured its value at time t1, and after some time at time t2, measure the current of the same branch, okay, and add it from K is equal to 1 to B, depending upon how many branches are there in the network, will get 0. So these are the two properties of the Telgen's theorem. First one basically one is required to check the topology of the two networks. If this property is satisfying, then both the two networks N1 and N2 having the same topology. Now come to some problems. Verify Telgen's theorem for networks shown below. So what you have to do? What are the steps? What are the steps involved? If mark the number of nodes in the network, if it is not marked. Here it is marked A, B, C, D. Okay. Then apply Kirchhoff's current laws and voltage law. Kirchhoff's current law and voltage law to find the branch voltage and currents. So current and voltage and current across each branch. So how many branches are there? Suppose 1, 2, 3, 4, 5, 6, 7. So 7 branches are there. So applying Kirchhoff's voltage law and current law, find the all branch voltages and all branch currents. First step. Then take the product of branch 1, Vk Ik means K is equal to 1 to 7. So here we can have this K is equal to 1 to 7 Vk Ik. So if you expand this will coming V1 I1 plus V2 I2 plus V3 I3 plus V4 I4 plus V5 I5 plus V6 I6 plus V7 I7. If it is coming summation coming 0, then this theorem is verified. So apply Kirchhoff's voltage law, because we can get this once the Kirchhoff's voltage law and current laws are satisfied. So apply Kirchhoff's current law, voltage law, we can write these two equations. Okay, on simplifications. So let here ADBD. So apply Kirchhoff's. I have written inside. Just erase these lines. So apply here, write apply Kirchhoff's voltage law in the loop DABD. You write, just write this line is missing. So start from D to A. So in the question the direction of the current is given. If not given, then you can orient the all the loops or meshes of this network. So from D to A, the current is moving like this. Here is plus, here is minus. So I am moving from plus to minus. So it is minus 6I1 voltage. Okay. Then A to B. So A to B, what is the current? Current is, if I am considering I1 minus I3, because I1 is going from A to B and I3 is coming from B to A. So a differential will flow through 3 ohm resistor. So if I am considering I1 is greater than I3, so I1 minus I3 will flow from A to B and I3 minus I1 will flow from B to A. So if I am considering the I1 minus I3, it means I1 minus I3 will flow from A to B. So here plus and here minus. So it is potential drop. So what will be? Minus 3 I1 minus I3. So it is minus 3 I1 minus I3. Then B to D. So B to D, here is the plus terminal of the voltage source. So from plus to minus, we are going from plus to minus. So there will be a potential drop. So it will be a minus 4. So this is the first equation we can get. Similarly, we can get the second equation. So 2 minus 2 plus, so 2 minus 2I3 minus I3 minus I2 is the current through this one. Okay. So I3 minus I2. So I2 is flowing from B to C and I3 is flowing from C to B. So if I am considering I3 is greater than I2, so it will be here plus, here minus. So minus I3 minus I2 and minus 3 I3 minus I1. So here basically we can write apply Kirchhoff's voltage law in the loop A, then this say this is E is not there, so E, then C, then B and then A. So basically there are 3 unknowns, so you have to write 3 equations. So bus, this is the your Kirchhoff's voltage law. Just rearrange all the variables and we can get this equations. So I1 in terms of I1, I2, I3 is equal to 2. So this is the second equation. Here we can apply the Kirchhoff's voltage law. So apply Kirchhoff's voltage law in the loop. Don't forget to mention this, okay? D to B, D to B, so dV, then B dVc, then D. So in this loop, so basically Kirchhoff's voltage law in this loop, and this loop. There are three independent loops or three meshes. We can write the three independent equations. So we can get here in terms of I1, I2, I3. So this is here I1 is not there, so this is the. So there are three unknowns I1, I2, I3 and three equations. So we can solve these three equations to get the value of I1, I2 and I3. Okay. So these are the values of I1, then I2 and then I3. Okay. So what are the steps? First identify the number of nodes in the network. Then apply Kirchhoff's voltage law, because you have to find the current. Okay. So once you have written all the equations, so by solving these three equations, we can get the three variables. There are three unknowns, so you have to write the three equations. Okay, once we get here, we can see that here the I1 is minus, and in the network it is taken as clockwise. So direction is magnitude is coming minus 1 by 64. It means the direction will be anti-clockwise. So just for a better understanding, or just it is convenient just to redraw the circuit with the proper current direction. Okay, to just avoid any ambiguity or any confusion, you can redraw this circuit. Okay, with the proper direction of the currents I1, I2 and I3. Okay, so here I have just drawn this here. So there are 7 branches, V1, so V1, I1, V2, I2, V3, I3, V4, I4, V5, I5, V6, I5, V7, I5, V7, I7, you have to calculate from this network. Okay. So what is V1? V1, so V1 is I1 into 6, so this is 6 ohm, this is 6 ohm, so it is 2.23. So V1 we have calculated, I1 we have got from the Kirchhoff's voltage law, so we can get V1. Then V2, so V2 is the voltage across this, so this is basically 9 ohm, this is 9 ohm. So 9 into current, so it is coming this one. V3 is the voltage across this. Okay. So it is 2 into I3, so this is the 2 ohm. Impedance is 2 ohm. 2 into I3 we can get. So V1, V2, V3, I1, I2, I3. Okay. Now come to V4. So V4 is the voltage across this. So voltage across this means just multiply the resistance of this resistor, that is 1 ohm, and the current is I2 minus I3. I2 minus I3, so it is coming this one. So this is your V4. So V4 and what V4 and then and I4 will be, what will be the I4? I4 will be the differential of V2 and I2 and I3. So this is your I4. Then V5 is this voltage. So we can see that now I1 and I3 same direction. So 3 into I1 plus I3. So this is basically your I5 and this is your V5. Similarly V6 is this voltage, supply voltage. It is given in the problem. This is of 4 volt. Okay, and I6 is, we can see here, I1 is moving like this and I2 is moving like this. So current through the this V6 is I1 plus I2. So it will be this one, this much. So suppose one thing I am just and one is V7. V7 is 2 volt. So it is 2 volt, and I7, because both are in series, so I7 is I3. So I7 and I3 is this one. Suppose this is your voltage source, okay, and this is the plus and this is the minus. If the current is coming out from this voltage source, so in this case the power will be power positive, means this source is supplying power to the network. Suppose it is coming like this. Suppose this is your 5 volt, this is your 5 volt. So in this case power is negative. Negative means this source is absorbing power, okay. So this convention you must remember, okay. Here look at minus to plus. So current is leaving the plus terminal of the voltage source. So it is I1 plus I2. So it is delivering power, okay. This voltage source I3 is coming out from the plus terminal of the voltage source. So it is power delivering to the network, okay. So power will be positive. So once we have calculated all V1, V2, V3, V4, V5, V6, I1, I2, I3, I4, I5, I6 and I7. Okay, all the branches is currents and voltages. Then we can apply this theorem. So basically this is your Thevenin's theorem. So K is equal to 1 and 7 is the number of branches. Vk, Ik is equal to 0. You have to prove. You have to prove. Okay. So K is equal to 1 to Vk, Ik. So V1, I1, V2, I2, V3, I3, V4, I4, V5, I5, V6, I6 and V7, I7. I have written here all the plus sign, summation sign, okay. But we remember there are two types of components in the network. One is the energy supplying, that is we have the two voltage sources, okay, and the remaining are the resistor of the network. So if you take, for sign convention, if you take the power delivered by the voltage source positive, then the power consumed by the resistors or load will be negative. Clear? So there are two voltage sources. I think that this V4 and V7, if I am not wrong. These are the two voltage sources. Okay. This sorry, V6 and V7. V6 and V7. V6 and V7. So if you take this is as a positive, if it is positive, then remaining will be negative, or if this is negative, then this all will be positive. So here you can see I have taken this. So plus here positive. So power supplied by source, this is the power supplied by source, okay, and this is the power consumed by resistors, positive, or vice versa. We can take this positive and this negative. So we are getting this. So differential is very small. It is coming 0.0032. That is equal to 0. So if you are getting summation, algebraic summation of this all the voltage and currents, product of the voltage and currents, we are getting 0, it means the theorem is verified. If it is not, then the theorem is not verified. Come to the another very typical problem just here. Verify Telgen's first property for the circuits given below. So there are two networks are given. Say this is your N1 and this is your N2. N2 network. This is your N1 network. Two networks. And it is also given that this network V1 is 4 volt, V2 is 2 volt, V4 is 3 volt, and I1 2 ampere, I2 2 ampere, and I5 is minus 6 ampere. Yeah, minus 6 ampere. For the network N2, V1 5 volt, V2 0, V4 2 volt, I1, I2, I3. So out of this, there are 6 branches in the both the networks. Some of the voltages and currents of the some branches are given. Okay, and you have to verify the first property. So you must remember what is the first property of Telgen's theorem. It will be not given in the numerical or examples or in the test. So you have to remember what is the first property of Telgen's theorem. So what is the first property of Telgen's theorem? This is the first property of Telgen's theorem. So you have to verify this and this. If it is coming 0, okay, V1k into I2k over k is equal to 1 to B 0, and V2k and I1k over k is equal to 1 to B, if it is coming 0, then this theorem is verified. So some of the values are given, you have to find the remaining. Okay. So what we'll do? Just I am giving some hints here. Suppose for network N1, V1, V2, this voltage and this voltage is given. So just apply Kirchhoff's voltage law in this loop. So mark this A, this is B, C, say this is your D. Okay. So apply Kirchhoff's voltage law in the loop A, B, C, A. Okay. So A to B, V1 minus 2 plus, so it is V1. Then here plus to minus, so minus V2, plus to minus V3 is equal to 0. So V3 is V1 minus V2. What is V1? It is 4 volt. What is V2? 2 volt. So it is 4 minus 2, so 2 volt. So basically you have to apply Kirchhoff's voltage law and current law to find the voltages and currents of remaining branches. Okay. So we can get the V3 we can get. Okay. Then once we have V3 is known, now what about other V4? So apply Kirchhoff's voltage law, apply KVL in loop AC DA. Okay. So A to C, so minus to plus, so V3. C to D, plus to minus, so minus V4. D to A, plus to minus, so minus V5 is equal to 0. So V3 you have obtained right now, it is 2, or V4 is given. How much V4 it is? Minus 3 is equal to V5, that is minus 1 volt. V5 is minus 1 volt. Okay, so this way we can get. Then for the remaining branches, so just I'm just saying. So we have obtained V3 is equal to V3. We have obtained how much? It was 2 volt. V5 we have obtained. V5 we have obtained how much? V5 it was minus 1 volt. Now V6. So V6, what we have to do? Apply. V2 is known. V4 is known. Now we apply the here. Again, just write B, C, D. So apply Kirchhoff's voltage law in the loop. BD, one we can mark here, BD, BD, B2D, then C, B. So B2D, so minus 2 plus, so V6, minus 2 plus V6, D2C, minus 2 plus, so it is V4, then C2B, so C2B is minus 2 plus, so V2 is equal to 0. So V4 is, so V6 is nothing but V2 minus V2 plus V4. Okay, take the minus outside. So it is coming minus V2 is 2 volt. So 2 plus 3. So it is coming minus 5. So I have obtained all the voltages. Now come to the currents. So current you have to apply Kirchhoff's KCL. So look here, I1, I2 and I5. I think I5, yeah, it is I5. It is I5. It is I5. Okay. A given. So look at here. Here is I1, I2. Okay. And I5. These three currents are given. So what will do? Apply Kirchhoff's current law. Apply Kirchhoff's current law at node B. Apply Kirchhoff's current law at node B. So I1 is away, I2 is away, and so I6 is equal to I1 plus I2. What is the Kirchhoff's current law? Algebraic sum of current meeting at a node is 0. So it means incoming current equal to the outgoing. So I1 and I2 they are away from the node B and I6 is approaching node B. So I6 is equal to I1 plus I2. So I1 and I2 is given. So it is 2 plus 2. So it is 4 ampere. Okay. Now is 6 is known, I2 and I5. So I2, I5, I6, I3 is not known. So what we'll do, this is known, okay, I5 is known, it is given, and I6 we have calculated. So what now the next step is apply Kirchhoff's current law at node D. Apply Kirchhoff's current law at node D. Here we apply, okay. So I4 is approaching, I6 and I5 are leaving. So I4 is equal to I5 plus I6. So I5 is leaving. So how much leaving? It is leaving minus 6. Okay. Then and I6 is 4. So how much? It is minus 2. Okay. I5. Then we have obtained I4. I4 obtained, I5 obtained, I2. So now unknown is I3. So I3 apply Kirchhoff's current law. at node C. So I2 approaching and I3 are leaving. So I2 is equal to I3 plus I4. Why it is so? Because I2 current is approaching node C, whereas I3 and I4 they are leaving node C. So I2 is equal to I3 plus I4. So I3 is equal to I2 minus I4. How much I2? I2 is 2. Or how much I4? So minus 2. So it is 4. Then what is the current through this? V4. I4 we have obtained, I5. So I1, I2, I3, I4, I think we have obtained all this. I1, I2 given, I3 we have obtained, I3 we have obtained right now. So this is I3. I4 we have obtained, I5 is given, I6. So we have calculated all the voltage and currents. This is the for the network N1. And we can carry out the similar approach to find the all the branch voltages and all the branch currents in the same way of this network N2, and then apply the first property. I am just leaving it to you. Just find all voltage and currents of this network. Okay. Then take B1K. So you take K is equal to 1 to 6. B1K, B1K, I2K means network N1 and N2, and it is coming this, and K was equal to 1 to 6, B2K, I1K is equal to 0. So you have to verify this one. So obtained all, just calculate all the remaining voltage and currents of this network N2. We have obtained N1. Applying the same concept, Kirchhoff's current law, voltage law. Just you have to just suppose V1, V2, V4 is given. So apply voltage. This V1 is equal to V3. This is V2 is 0. Means V1 and V3 they are in parallel. So V3 is how much? V3 is 5 volt. Okay. Then V3, V4, V5, apply Kirchhoff's voltage law in this loop. You can get V3 we have obtained, V4 is given, V5. So apply this KVL in this loop. In this loop you can obtain all the remaining voltages. Then applying Kirchhoff's current law, okay, you can obtain all the voltage and currents of this network. So this way we can verify. So I am just leaving to you. Apply Kirchhoff's current law and voltage law to get the all remaining branch voltage and currents of this N2, and just try to do this. If it is coming, then the first property is verified. If it not, then the first property is not verified. So thank you very much. If you have any problem, you are not getting, then you can write mail to me. I will give the complete solutions. But you do yourself. Without doing, you cannot learn. So for the learning point of view, just I am leaving calculation of all the variables of N2 network, and then apply this to verify the first property of the Tilden theorem. Okay. Thank you. Jai Hind.